So we are continuing on the lecture on Henry's law and Raoult's law. So we discussed on Friday that before we could state Raoult's law, we had to have an idea of what an ideal mixture is. So we discussed a little bit of some characteristics of an ideal mixture. So we'll continue from there before we get to stating the Raoult's law. Ideal mixtures and enthalpy change of mixing. So this is what we're looking at today. When you make any mixture of liquids, you have to break the existing intermolecular attractions. I hope you can remember that when we're talking of solutions, solute in solutions, we mentioned that there are some intermolecular attractions between molecules, either between the similar molecules or the different molecules in the solution. We're talking of ideal mixtures. So for you to make any mixture of liquids, you have to break the existing intermolecular attractions. And this needs energy. So, and then to remake new ones, energy is released. So if all these attractions are the same, there won't be any heat exchange. No heat is evolved, no heat evolved, no heat absorbed. That is in an ideal situation. So if all the attractions remain the same, as I explained to you on Friday, now that means that it's an ideal mixture of two liquids. So then you will have zero enthalpy change of mixing. That is, no heat evolved, no heat absorbed. So if the temperatures rise or fall when you mix the two liquids, then the mixture is no longer ideal. That means heat is absorbed, it is evolved. It means the forces of attractions are no longer the same. And so that makes the liquid mixture not to be an ideal one. So, and then we want to state Raoult's law based on our understanding now of ideal mixtures. There are several ways of stating Raoult's law depending on the situation you're talking about. So let's look at, we have Raoult's law as applied to non-volatile solutes. We also have Raoult's law as applied to two volatile liquids. So now let's look at Raoult's law as applied to two volatile liquids. Please mute yourselves. Mute yourselves. So looking at Raoult's law as applied to two volatile components, the partial vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component at that temperature multiplied by its moles fraction in the mixture. We're stating Raoult's law. Who is the person that is still making noise there? Can you mute yourself?
Being an appetizer. Yes, the opportunities available to us are limited. Opportunities now.
Mute yourself. Who is the person still talking?
Like, see, you don't know that you can also make it to the desert.
Fumilayo. Can somebody stop Fumilayo from talking there?
Don't know what
If anybody is there close to Fumilayo, please stop her from making noise here. So let's continue with our lecture. I hope you all know that this lecture is recorded. So when you make noise and your name is mentioned, it will be recorded. Okay, so let's take Raoult's law again as applied to two volatile components. It says that the partial vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component at that temperature multiplied by its mole fraction in the mixture. So let's see what this means. Look at this equation. It's for a mixture of liquids A and B. So you have liquid A and liquid B being mixed together. Now you have PA is equal to XA multiplied by P0A, that is for liquid A. Then for liquid B, PB is equal to XB multiplied by P0B. In this equation, PA and PB are the partial vapor pressures of the components A and B. PA and PB are the partial vapor pressures of the components A and B, which when you combine these two partial vapor pressures of the different components, you will have the overall vapor pressure, no longer partial. You have the overall vapor pressure in that mixture. So the total vapor pressure of the mixture is equal to the sum of the individual partial pressures. Like I showed you in the previous slide, for the two different liquids, the different partial pressures, PA and PB. And I showed you that PA is the partial vapor pressure for liquid A multiplied, which is equal to XA. XA is the mole fraction of liquid A multiplied by POA, which is the vapor pressure of that liquid when it is on its own without being mixed. So we'll understand it as we go. So, but now for you to get the total vapor pressure in that mixture, you have to add the vapor pressure of liquid A, that is partial vapor pressure of liquid A, to the partial vapor pressure of liquid B to give you the overall vapor pressure of that liquid mixture. Here, in that equation I showed you here, PA is equal to XA multiplied by POA. PO is, the PO values are the vapor pressures of A and B if they were on their own as pure liquids. PO for A is the vapor pressure of liquid A as it is on its own without putting it in another mixture, just on its own as a pure liquid. And then the PO B is the vapor pressure of B if it is on its own as a pure liquid. So you can now, I believe you know the difference between PA and PAO. PA is the partial pressure of liquid A in the mixture. That is the pressure that liquid A is contributing in that mixture. So it's the partial pressure. PA is that. So PAO is the vapor pressure of that liquid A when it's on its own as a pure liquid, when it's not in a mixture. So now, XA and XB are the mole fractions of A and B. That's exactly what it says here, that the fraction of the total number of moles present, which is A or B. I think you will understand here as we go. So you can calculate the mole fraction using this example. XA is the mole of A divided by the total number of moles. So if you have liquid A and liquid B in a mixture, then for you to know XA, you know that a certain number of moles of A is mixed with a certain number of moles of B that is in that mixture. So for you to have your XA, the mole of A divided by moles of A and B added together. The moles of A divided by the sum of the moles of A and B. That's the total number. So that gives you the mole fraction for A. For B also is the mole of B divided by the total number of moles, that is the mole of A and B together. Mole of B divided by the combination of that of A and B. That gives you the mole fraction of B. So now let's look at an example here to make it much clearer to you. So suppose you had a mixture of 2 moles of methanol and 1 mole of ethanol at a particular temperature. The vapor pressure of pure methanol at this temperature, say it is given to you as 81 kilopascal. And the vapor pressure of the pure ethanol is 45 kilopascal. Now you see there that we have 3 moles in the mixture. That is 2 moles of methanol and 1 mole of ethanol, making it 3 in that mixture. So now for methanol, 2 of the moles of methanol, for you to get the mole fraction for methanol, it is 2 of methanol divided by 3. 3 is the sum of that of methanol and ethanol in that mixture. So similarly, for mole fraction of ethanol, it is 1 divided by 3. So that 1 of ethanol divided by the total there, which is of the methanol and ethanol. So you can easily find the partial vapor pressures using Raoult's law, assuming that the mixture of methanol and ethanol is ideal. That is, all the molecular attractions are the same. So now, for you to just use this, use the equation here. P ethanol is equal to X ethanol multiplied by the vapor pressure of ethanol when it's a pure, on its own pure state without mixing with anything. So P ethanol is the partial vapor pressure of ethanol, which is equal to 1/3. That is the mole ratio of ethanol multiplied by P, that is vapor pressure of ethanol as a pure liquid when it's not mixed. So with that, you can get the partial pressure of ethanol as 15 kilopascals. So you do the same for methanol, and then you have the partial pressure as 54 kilopascal. And so now the total vapor pressure in that liquid, in that mixture, is now P ethanol plus P methanol, which is 54, and which is 15 plus 54, that gives you 69 kilopascal. So this is how you can calculate the vapor pressure. So I believe you now know the difference between the partial vapor pressure and total vapor pressure. So now the vapor pressure, we're looking at Raoult's law as applied to non-volatile solutes now. What we looked at before was that as applied to volatile components, two volatile components, where you can combine the two partial pressures to get your vapor pressure using their mole fractions and the vapor pressures at their pure state. So now you go to, we're looking at Raoult's law as applied to a non-volatile solute. So the vapor pressure of a solution of a non-volatile solute is equal to the vapor pressure of the pure solvent at the temperature, at that temperature, multiplied by its mole fraction. So here we're looking at the pure solvent. The pure solvent plays a very great role here. So that's the vapor pressure of the solution, which is P, talking of that of a non-volatile solute. The vapor pressure of a solution of a non-volatile solute is P, and that P is equal to the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. This is the equation. It's different from that of volatile solids mixtures, where you have different components coming together and their partial pressures. So PO is the vapor pressure of the pure solvent at a particular temperature. So X sub here is the mole fraction of the solvent. That's exactly what this says, that the fraction of the total number of moles present, which is that of solvent. You calculate it using this equation. So for you to have your mole fraction of the solvent, which we need when we want to calculate the pressure of the vapor pressure of a solution of non-mixture, the mole fraction of the solvent that is important here that we need can be obtained by using this formula: moles of the solvent divided by the total number of moles. Mole of the solvent divided by the total number of moles. I mean, total number of moles here, you have mole of solvent plus the mole of the non-volatile solid. So for you to have the mole fraction of the solvent, you can use this formula: mole of solvent divided by total number of moles. So there are some examples here I want to show you, but I want us to do it here in class. I want to do just one for you, and then the rest, the other two, I'm not doing them. From this one I'm solving, I strongly believe that you'll be able to solve the other two. So let's look at this one. 80 grams of glucose was dissolved in 100 mils of water. What is the expected vapor pressure of this solution at 25 degrees centigrade? Given that the vapor pressure of water on its own, the pure water without any solid in it, at 25 degrees centigrade is 0.0317 torrs. So what is the expected vapor pressure of this solution? Now you go back to that formula I gave you, which you can use to calculate the vapor pressure of a solution, a solution of non-volatile, a solution of non-volatile solute. So which is here, go back there to show you. So you can jot it, put it down, write it down, so that you can use to calculate, because I'm going to ask you to calculate the other two right here. So write this one down. P is equal to X solvent multiplied by P0 of solvent. That is what you will use. And also don't forget that X solvent, that is the mole fraction of solvent, is equal to moles of solvent divided by the total number of moles in that solution. So using that now, we want to calculate, we want to find out what P will be. P. So first of all, we have to know the mole fraction of the solvent because we have been given the vapor pressure of the pure solvents, that is of the pure water. So we want to know the mole fraction of the water. So in this case, how do we know this? We have been given 80 grams of glucose to dissolve in 100 mils of water. I want also to bring to your attention that water here, we're taking it as, 100 mils at 100 grams. So far, we've been doing that. 100 mils as 100 grams. So take it that this is 100 grams of water. And so now, what do we do first? We want to see the mole fraction of the water. And we are told, so first of all, let us know what is the mole, how many moles of glucose is actually here. So we will be given 80 grams of glucose. Let's find out the moles of glucose here. So can somebody calculate for me? How many grams
0.234
are there in 1 mole of glucose? How many grams?
0.234 mole.
You say what?
0.234 mole.
0.234 mole.
Yes, sir.
Okay, now, how many grams do we have? What is the molar mass of molecular weight of glucose?
342.
300 and
42.
say what?
342.
342. Okay, so that now you from there you should be able to know how many moles of glucose that you're working with. So you told me it's how many?
0.339.
0.234 mole.
It's like you're having different answers, which shouldn't be.
0.234.
You know, okay, now your carbon is 12.
0.239.
Okay. All right, you're right. Okay, now you have 0. What? 339.
Yes. 0.2339.
Yes, 2339. Okay, yeah, that's like 240. So 239. Okay. All right. So now with that, you know the moles of the number of the moles of you know the moles of glucose here. Now, what of that of water? Because from the equation from the formula here, the X, that's mole fraction of the water is the moles of water divided by the total number of moles. Now we have the moles of the glucose. So what of that of water so that we can add there? So taking it as, take that moles is mass over molecular mass. Is that? Moles is mass over molar mass. Mass over molar mass. So now mass of water, mass here is 100 mils, that is 100 grams, over molar mass, 18. So that will give you like 5 point something moles.
5.55 now.
Okay, yes, with that now, from the equation we have that X of water is the moles of water divided by the total mole. So so what do we have there now? 5.55 over 5.790.
Let's add it up. So
Okay.
that becomes
So now
plus
with that
5.555.
divided by 5.79.
5.55, not 0.55.
Okay. So that gives you what? 0.959 thereabout. So now you have the X for the water. So with that X for the water that you have, you can now put it into the equation for the vapor pressure of solution of non-volatile solutes. So you now have the vapor pressure, that is P is equal to X of water multiplied by P, that's the vapor pressure of the pure water. The vapor pressure of the pure water is given to us as 0.317. So now we have obtained the X as 0.959. So the P will be 0.959 multiplied by 0.317. Did you get that? So in this case, I think
0.599.
yeah. So you just multiply, just substitute it into the formula I gave you for non-volatile solids. So that's how you will be able to calculate that. Now, these other two, I'm not going to calculate them for you, but you will use the same. Here we are given glucose. How many grams of glucose must be added to 250 grams of water at 40 degrees centigrade to create a solution with a vapor pressure of 50 torrs. The vapor pressure of water at 45 degrees centigrade is 55 torrs. So I want you to attempt this. If you cannot successfully attempt it now because of time, because I have to move on, I'm going to load this lecture immediately after this class. I will load it on LMS so that on Wednesday, I want to see who has been able to calculate this. This is another problem I want you to also try. So you can see in this case, the mils of water, 225 mils, is also taken as 225 grams so for water. So this is another problem I would like you to try. We still have to move on because our time is going. So when you get home, you will try these two problems and let me see what you have in the next class on Wednesday. So now, this is another, so we see the effect of a non-volatile solute on the melting point and freezing point of the solution. We want to look at the effect of non-volatile solute on melting and freezing point of the solution. So the boiling point of the solvent in the solution is higher than that of the pure solvent. Note that the boiling point of the solvent in a solution is higher than that of the pure solvent. What that means is that if you just have your water as solvent, for the pure water, the boiling point of water, you know what it is, 100 degrees centigrade. So when you add something, you add solute to water, the boiling point will be higher than what you have for pure water. And for the freezing point, freezing point becomes lower than that of the pure solvent. If water freezes at 0 degrees centigrade, by the time you have added a solute to that water, the freezing point will become lower than that of the pure water, not just for the water, for any solvent. When you add solute to it, the freezing point will be lower, and for boiling point, it will be higher than the pure solvent. So now let's look at the boiling point elevation. Boiling point elevation, that is delta T, boiling point, increase temperature. So the boiling point elevation delta T, boiling point, is directly proportional to the molality of the solute. Boiling point elevation delta T is directly proportional to the molality of the solute. I'm not talking of molarity, I'm talking of molality. There's a difference between molality and molarity. I believe you know that, but let me just remind you that molarity is the number of moles of a substance per liter of solution. And so it can also be referred to as molar concentration. But molality is the number of moles, the number of solvent moles per kilogram of the solution. The number of solvent moles per kilogram. So it's different. It's different. So now let's look at the boiling point elevation, which is called molar boiling point elevation.
Okay, some people, they never live with their husband before.
You have the equation, whoever is talking, I will check you and call your name. So wherever this lecture is presented, your name will be called therefore as a noisemaker. So it's better for you to just keep quiet, mute yourselves. So now, you see the delta T, the boiling point elevation here is delta T, boiling point, which is equal to K boiling point multiplied by M of the solute. K boiling point is the molar boiling point elevation constant by solvents at degree centigrade. So here, at what temperature? It's per molar concentration. So now, how many grams of ethylene glycol do you have to add to 120 grams of water to increase the boiling point by 1 degree centigrade? Here, the molar boiling point elevation constant for water is given as 0.5121 degrees per molar. So it's likely you will do this also at home and bring it back to me because of time. So, and let's see, for the freezing point is just similar to what happens to the boiling point. So for the freezing point, the delta T, this is change in the freezing point, change in the temperature for freezing point is equal to K freezing point multiplied by M solute. We're talking of the molar concentration, which is the number of solvent moles per kilogram. So the reason for this is very similar in changes in vapor pressure equilibrium. Reason for this is very similar changes in vapor pressure equilibrium. There are more atoms per pure solvent going from solid to liquid than from liquid to solid. So we're talking of vapor pressure equilibrium. So there are more, the depression here, the reason for the freezing point depression is that there are more atoms of pure solvent going from solid to liquid than from liquid to solid. So I've told you about an ideal situation where you have all the forces, molecular forces being equal. What I mean by that, the forces of the different solutes being equal to the forces, intermolecular forces of the different solutes being equal to molecular forces of similar solutes being equal to, like I said to you. So all the forces are the same. But in a non-ideal situation, like we said before, it is not so. So solutions that do not obey Raoult's law are called non-ideal solutions. There are differences in the molecular attractions between molecules in the solution. That is a non-ideal solution. So that means that all ideal solutions obey Raoult's law. All ideal solutions obey Raoult's law. Non-ideal solutions do not obey Raoult's law. And I hope you remember Raoult's law. So in case you have some questions, you will be given some questions that which type of solution obeys Raoult's law. I believe you should be able to know. Solute-solvent interactions are significantly different from solute-solute and solvent-solvent interactions. That is in the case of a non-ideal solution. You know, of course, in ideal solution, solvent-solvent interactions are the same with solute interactions are the same with solvent-solvent interactions. So everything remains the same. No change, no heat change, no change in enthalpy. The enthalpy change is 0. Those are in ideal. Non-ideal is not so. So intermolecular forces between components in a dissolved solution can cause deviations from the calculated vapor pressure. That is in a non-ideal solution. So that is why they do not obey Raoult's law, because they can cause deviations from what the vapor pressure is supposed to be because of the difference in interactions. So still on deviation from Raoult's law. So if the vapor pressure of a mixture is lower than expected from Raoult's law, this is said to be a negative deviation. If the vapor pressure of a mixture is lower than what is expected from Raoult's law, we will see what is called negative deviation. It is lower. On the other hand, if it is higher than what we expect from Raoult's law, then we have a positive deviation from Raoult's law. Of course, what we expect from Raoult's law is an ideal situation. But when there is a deviation from ideal situation, it means it could go lower than what we expect, that is negative, or it could go higher than what we expect, that is positive deviation. Of course, what we expect is an ideal situation. But remember that I've told you before that actually real ideal situation doesn't exist. but we look at situations that are quite close to ideal and assume and take it as ideal. So this means that there are possibilities of you having some deviations, because no situation is perfectly ideal. So you can either have a negative deviation or positive deviation. Negative when the vapor pressure of the mixture is lower than what is supposed to be in ideal, and positive when the vapor pressure of the mixture is higher than what we expect to be in ideal. Okay, now we want to see a boiling point diagram of binary mixture, binary miscible liquid mixture, binary miscible liquid mixture. I gave you an example of heptane and hexane before. So such miscible mixtures. So liquid with high vapor pressure, we have low boiling point. These statements are the statements that you should note very well and understand, because I don't want you to get confused when you're in exam hall. So note it very well that liquids with high vapor pressure will have lower boiling point. Also note that liquids with low vapor pressure will have higher boiling point. I hope you have not forgotten also the negative deviations when vapor pressure is lower than expected, and the positive deviations from Raoult's law when the vapor pressure is higher than expected. So now let's look at the diagram here. When we have positive and negative deviations from Raoult's law. When you have the boiling point here of pure liquid B on the left axis here, and on the right side you have the boiling point of the pure liquid A. So then when you mix them, there's a tendency of positive deviation and also of a negative deviation. You will have the positive, this explanation will continue in the next lecture. It will continue in the next lecture. So I want to give you time to ask some questions because we have just 4 minutes left for us in this lecture. So more explanation of this chart will be given to you on Wednesday in the next lecture. So you can raise your hand if you have questions to ask. You can raise your hand if you have questions to ask. I don't want noise, just raise your hand so I pick you. If you make noise, and then of course, this lecture is recorded. So just raise your hand. Okay, Bankole, you can ask your question.
All right, ma. I just want to ask when we are going to get the slides, like the solution and solubility slides. We've not gotten any slides so far.
You say what? You've not gotten any slides?
This,
no, I've given you
yes,
all.
it's just the video.
Your colleagues have seen it. You've
It's not yet on LMS.
LMS.
It's not on LMS, man.
It's on LMS.
It's not on LMS.
It's only the link to the video.
It's just the videos.
That's the video. That's the lecture. The lecture,
yes,
because the lecture is recorded.
Yes.
It's easier.
No,
it's easier for you. Can you keep quiet a bit? Let me explain. I think it's easier for you because the same lecture I would have just sent to you is okay? You want just only the recorded lecture. You want the PDF as well. Yes, ma'am.
Yes, ma'am.
Okay. All right. I think what I will do, I will also upload the.
Don't pass gas.
I will also.
Now after solubility, let me hear this. This one under gas will be like this.
Can you listen?
Under round four, now will be like this.
Can you listen? I will also upload the PDF lectures to you on LMS. I was thinking this one is okay for you because this one carries all the explanations and the questions you're asking and the answers. So who is the person talking now? Timothy, why are you talking? Omotayo. Why are you talking? I didn't call you to talk. Festus has raised his hand. I will call him to talk. But why are the other people disturbing? Please don't disturb the class. I've called your name. So when anybody is playing this, is watching or is listening to this, they'll be listening to your name as making noise. So please don't make noise. Now, I was thinking this lecture is okay for you as it is recorded because questions you're asking and the answers I'm giving to you and the examples that I'm doing calculations for you also, explaining to you how you do the calculations, I thought this would be better, but no problem. In addition to this, I will also upload the PDF of the lectures to you on LMS. I think that is okay. So do you, somebody else had a question, Festus? Yes, Festus.
I wanted to yes, I wanted to slide.
Oh, okay, Festus.
Thank you very much.
Maybe you're talking about the slides. Yes, I will send and upload them also on the PDF on the LMS for you. So I think we're running out of time now. It's already 10 o'clock. Maybe I can take just one question for 1 minute. Any other question? So no other question. I'm going to stop sharing and then I will send this recorded lecture to you and then also send the PDF as well to you. So we'll see again on Wednesday. And when you're coming, please go and look at this lecture again and look at the lecture and the questions, the problems you need to solve, try and solve them. And then bring the solutions. Let's look at it. Let's look at what you have on Wednesday. Bye-bye.
Thank you. Bye, ma. Bye, ma.
Bye.
Thank you.